Thank you. Thank you. Now, today, although we have a very short period, we are just going to continue still with the concepts of the exponential functions. But this time, we are just going to introduce a new, I should say, concept, which involves the fact that, for example, you do not only plot the exponential functions, sometimes you have the plot of the functions, you are curious to see what kind of mathematical formula is going to represent that plot. And that's the thing that we just want to discover today. I say that exponential functions, which is the topic of this short period today. Now, if you remember, as a very quick review of what we had, we said that logically, we said that we do construct an exponential function like this format. We say that function equals to a base. It is raised to a power, which the power itself is a function. And still you remember those constrictions that we imposed, that a should be a positive real number and a should not be equal to 1. This is the thing that we discussed about that so far. And also we said that in order to make the things a little bit easier, the function that is going to be as an exponent of this exponential function, we do not take it to be a very complex function. We take it a linear function like ax. Then as a result, we said that at this level, we consider this function as a coefficient a, which is a real number itself, is multiplied to a base, which is also is raised to a power x. And that's the reason we call that exponential function, because you see that the function, which is a single variable function x, is at the exponent of the function. Now, as an example, in how to plot this function, I'm just going to do one quick example. I say, okay, I'm just going to give you one function, and the function is going to be this y equals to, let's say, for example, 2 times, let's say, for example, pick up a number, for example, 3, which is raised to the power of, let's say, 2x. We said that the thing that we are interested to do is that we want to plot this function. But first of all, based on all the things that we have learned, we notice that this represents an exponential function, and also it satisfies the requirements that the base has to be a positive real number, and this is not equal to 1. Thanks, Matthew. Now, in order to plot this function, we are going to plot this in the Cartesian frame. I construct 2 axes, that one of them is x, the other one is y. That's why it's going to be a Cartesian frame. That's the starting point. But in order to plot any exponential functions, Celia, like this, we have to follow 2 very basic methods. Method 1, step number 1, I should say, is that, first of all, we have to identify 3, I call that key points of this plot. And if you remember, we said that in order to find these key points, what do we do is this. I'm just going to, for example, construct a chart here. Then I'm going to say that, okay, for example, if this is going to be x, this is going to be y with respect to the functions that we have. Normally, we notice that the key points that we are going to choose is the ones that makes it easier. For example, if you introduce it as an x, it's going to be the easiest one to find the value of the y. One of the easiest point is what? Is going to be, for example, let's see if the source is back. Yes, we see that if x, for example, is taken to be 0, yx can be 0 because we noticed that if you remember from the previous sessions, we said that for any exponential functions like the one which we have here, what is the domain? Is R. It's all the real numbers. Then as a result, we say that they have no restrictions to finding the values for the x because every value is welcome mapping, including x0. Then if x is 0, what do we get, Elisa, here? We said that it becomes like this. We just want to find it. We say that 2, the value of the y is this. 2 times power times 3, and 3 is raised to the 2 times 0. How much is that? 2, because 2 times 0 becomes 0. 3 to the power of 0 becomes 1. 1 times 2 becomes 2. Then as a result, the first key point that we were able to find, it was so easy. And this is 2. Another key point, which is going to be so easy always to find it, is normally is going to be 1. This is going to be another point. We call that, for example, if x is equal to plus 1, what is the value of the y? It's going to be very easy. We said that the y, if x is equal to 1, I'm going to do a kind of a writing here. I'm going to erase that. I'm going to write it just to tell you, just to show you how do I get to that point. I have 2 here. Then I have 3, which is raised to the power 2 times 1, becomes 2 equals to 3 times 2, becomes 2 times 9, becomes how much? 18. That's right. Now the value becomes 18. Now, the next step is we need at least 3 points. Let's go to find the third one. Normally the third one, it becomes a kind of a symmetry with respect to the 1. That's right. Thanks, Elisa. We choose -1. What is a -1 if I just put there? I'm just going to do the right thing here. We said that then we have y. If x is equal to -1, what is that? It becomes 2 as an exponent, which is multiplied to 3, which comes as a base. I have 2 times -1. Hi, Sabrina, no problem. Then what do I get? I get 2. I get 3 times the power -2. You remember we introduced one very important identity. What was that identity? We said that a to the power -p, thanks Elisa, becomes 1 over a to the power p. That was a method, the identity. We talked about the exponent's law, that if you have an exponent, which quite surprisingly comes with the negative exponents, it's a trouble. How to get rid of the trouble? You bring it all the way to the basement, I mean the denominator, and flip the negative of the exponent to the positive. That's what was the identity about. If that's the case, I'm just going to do the same thing here. Look at this. I have, Matthew, you have a question? No? Awesome. Then you have -2 here as an exponent. It's a trouble. Then I use this identity to bring it down. I get 2 then times 1, 3 to the power +2, which is 2 times what? 9. Does it make sense to everyone?
Yeah. Oh, yeah. Okay.
Because we have 2, we have 3 to the times 3 becomes 9, then we have 2 times 9. Now, then the third point is very easily found. 2.9. Yes, Janaya? Now this is the first step. The first step is complete. Let me erase this. The first step now is complete. Now, before we just go to the second step, let's localize and pinpoint these points along the Cartesian frame. The first point comes with the x equal to 0 and the y, which is 2. For example, roughly, it is going to be this point. It is going to be this point. For example, I call this point A. This is point A. The second point is a point, if I call this B, is a point which comes as x equal to +1, but its y is going to be, for example, +18. Imagine we are not very precise, but imagine this point is represented there. X is 1, y is +18. The third point is -1. Imagine that if -1 is here and 2/9 is going to be here. 2/9, you know that this is still less than 1. Then as a result, we imagine that this point represents C. Now, we have 3 points which represents this family of the function. Imagine that this is a huge family, 3 of them is going to represent that family. Now we have to connect them, but how? We just move on to the second step. At the second step, we said that we are gonna focus on the base of this exponential function Lucas of math here. And what is the base? The base is what? 3, which means that 3 is bigger than 1. You remember that when we talked about these exponential functions, we said that if the exponential function, I'm just gonna, as a review, go to the next page, write it here very quickly. We said that scenario 1 was the fact that our exponential function, which is represented like that, if a, the base, is bigger than 1, if you remember, we said that the function is increasing and it has this typical, I should say, plot. It was the case for a function which is increasing. This is for scenario 1. For scenario 2, we said that if the same exponential function, which is this, but the base, although we know that this is positive, greater than 0, but at the same time is less than 1. But in this case, we said that this function is typically represented like this. It comes from all the way, it goes to walk along the x-axis, goes to infinity. And that was a kind of a function. We said that this is decreasing. This one, a, is between 0 and 1. For this one is a is bigger than 1. Okay. Now, if I'm just going to follow these, I should say, principles, I go back to the same functions which I had. I notice that the base is greater than 1. It represents an increasing functions, which I know that it's going to looks like this, case scenario 1. Then at step number 2, when I notice that the base is bigger than 1, then I know that in order to plot, to connect these points, I have to follow the generic form of an increasing function. It means that, like the one which we had, I'm just gonna start from here, make sure that I be close to the x, because x is an asymptote, it's not gonna cross it. Then I cross C, I cross A, which is y-intercepts, and make sure that I cross B and go all the way up. Then as a result, you see that this is going to be the plot of the function, which is represented by 2 times 3 times base times the exponent of 2x. That's the review of what we did before we continue with the new topic. Any questions?
No.
Everyone is good?
Yeah.
Awesome. Now, and also we talked about the transformation. Today we do a very quick one also. Let's, okay. Let's do the transformation, a quick review right now. Then I introduce a new topic. As long as you are here, it's going to be much relevant when we do a review on the translation when we plotted these functions. Look at these functions which we had, and I plotted here. We'll look at that one as a mother function, as a very core function that the plot is easily done by first having 3 key points, then checking the base to see that if the function is increasing or decreasing. Now, the next thing that we do is this. I want to transform it into different formats to see that how the functions looks like. And for each one, I color code this. Now I'm just gonna do the transformation in blue, which it means that the one I'm gonna plot, it's in blue color. Let's now look at this function, which is gonna be taken from the parent function, but it's modulated. I follow the same core of the function. The exponent, the coefficient is 2. The base has to remain 3. But here I have, look at this, for example, minus 2x. Now, it's a kind of a transformation. Because we look at the functions which we have, the parent function, we know how to plot it. The only change which we incorporated is that we said that I'm just going to multiply x to minus. I'm going to go here to just list the transformations at what we have. It's a kind of a summary of the transformation. The first transformation that we have, as a review was this, we said that we have f of x, Celia, for example. We say that we transform this function from its parent function to this function, f of minus x, like the one which happened there. It means what? It means that, for example, if you have a function, you only change the x as a general. Normally, I remember this stuff from a basic functions that we have learned. For example, imagine if this is a parent function, square root of the x. We covered that before our summative test. When we are transforming, I should say, x to minus x, the function forms like this. The x that you had here, which you see that this is positive, if you transform x to minus x, you see that the function now has negative x. Then you see that the function is reflected with respect to the y-axis. We covered that maybe before the Christmas break. Now, in order not to confuse with its counterpart, we talked about this transformation. We said that we have f of x. This function is transformed to what? Minus f of x. Look at the position of the minus. Now this is outside of the f. We said that this one, as a general example, it's going to be like this. I myself, I remembered all these ones from a very basic functions that we have talked about. Now, for example, look at this. The same function. Square root of x. I always remember these methods just by taking one function into account. If I just want to have minus the square root of the x, it means that the value of the y is going to be negative. So far, the value of the y for this function, all this is positive. Then if I have minus the square root of the x, then the value of the x of the y is negative. You see that here is negative, and it's reflected by this one, by this minus. Then as a result, we learned that if minus Elisa is before the f of x, we reflect the function with respect to the x-axis. We take the x-axis as the mirror. Now, I go back to the same thing that we have. Compare these ones with those two rules. You see that the minus is acting on the x, not on the f. Then it means that the function has to be reflected to what? It's respect to the y-axis. That's right. Then the function, I'm just going to use this. Then the function, if it's going to be reflected with the y, look at this. The y is going to be taken as a mirror. It means that point B is looking at self at the mirror, he sees that he is standing here. It becomes B prime. Point A is just the mirror itself. The image of the mirror is the mirror itself. The mirror cannot see itself. Then the A and A prime are the same. But point C is looking at the mirror, he finds yourself here. For example, it becomes C prime. Now, it means that now that we just want to find the reflection, we are connecting these points together, like the one which we did before. And this, the blue one, becomes the transform function of these exponentials. Now, guys, what time the class finishes today? We have 20 minutes. Good. Now, look at the other transformation from the same parent function. However, this one, it's like that. We say y equals. Look at this time now. I'm going to introduce minus for the f of x, not for the x. I mean, I'm looking at the second transformation, which the minus Ella has gone into the f, not the x. It means that then as a result, I have this minus 2 times 3, and I have 2x. Now, what's happening there? You notice that with this transformation that the minus is acting before the f, the function is going to be reflected with respect to the x-axis. Then as a result, you see that the red function, which is a parent function, is going to be simply reflected with respect to the x. For example, you can see that the b is going to be, for example, here, we have b prime. A is going to be reflected here because now x-axis is the mirror, and C is going to be here. Everything sees the image of itself with respect to the x-axis, and you connect them as the way which we have done. You see that the pink plot represents this pink transformation. There were three typical transformation techniques that we can do on, I should say, on the exponential functions. Now, any questions, guys, so far? Everything is clear? Everyone is happy? Matthew, please. Thank you. Now, the people who are at home, any questions, Lex and Chloe?
No, all good. Thank you.
Everyone's good? Now,
Yeah, thank
if you
you.
have no questions, we stop this part of the lesson here. We move on to a new thing to discover. Before we just move on to the new thing, yes. Yes. Okay. This one or the previous one?
I'm not really sure.
You mean between the second, you mean the blue and the pink? Oh, no, there are two different things. Look at this. What happened, Chloe? Oh, sorry, Sabrina. Look at this one. The red function, which is here, it is going to be our core functions, the mother function, the parent function. The blue one is one kid, and the pink one is another kid. Then they are not related somehow. We just, for example, when we look at the pink one, we just compare that with the red one, which is the comparison between the parent and the kid one. Then at that moment, we forget about the blue one. Make sense? Good question. Now, okay. Okay, please quiet, Matthew and Lucas. Now, The next thing that we are just gonna cover at the end today with that, it's gonna be a very, very easy thing. Now, the thing is this, we are not gonna move backwards. So far what we have done, somebody gave us a mathematical representation of an exponential phenomenon. And what did we do? We tried to, for example, Daniel, to analyze it, plot it, to see how it looks like, to see what the kit of that exponential function looks like by transforming them. Now, what we want to do right now is that we want to move backward. We are going to have the plot, Kate, for example, and from that plot, we are just going to see what is the mathematical representation of that plot. That's going to be the strategy, Simon. Now, let's see how it works, because this one is going to be the much easiest one, the more easiest one compared to the first route that we had. For example, our general methods, always we construct the Cartesian plane. We have the y-axis, we have the x-axis, and we have here a kind of an exponential function. Okay, the exponential function. Right now, the thing is that I didn't have, I should say, a drawing paper. Then you cannot find the points on, you cannot see the points on the plot. But for your homework, for your assignment, for the test quizzes, you see that plot on a graphing paper that you can just measure the different, I should say, points of that function. Now, then as a result, I'm just gonna pinpoint the points on the plot myself. Guys, what is this strat? Yes. That's right. On the test, the number is given, or at least the plot is on a graphing paper, Janaya, that we can just measure the points that we want. Awesome, no problem. Now, what is the strategy? The strategy is this. Somebody has given me this plot, and they are asking me, can you figure out what is the mathematical representation of this pink plot? And that's the question. When somebody asks you that question, you say, oh, wait a minute. I don't know, because that can be a representation, Ella, of any function. But I tell you, we have a very important thing to remember. We notice that this function is increasing over the x-axis along its domain, which is the x. The function doesn't stop to increase. It grows as long as the x permits. This is a characteristic of an exponential function, that they increase all the time or they decrease all the time. There is no variation. There is no stop in between. Then as a result, Kate, we say that this function should represent an exponential function. Then our choices are limited. We cannot use a quadratic function. We cannot use a square root function, not a linear function, just an exponential function. Now, what is a skeleton? I mean, the skeleton, the structure, the skeleton of an exponential function. We say that it can be represented by a coefficient. It comes with the base, which we know that it has to be a positive real number, not to be equal to 1, and it is raised to a power x. Now, this is the skeleton of exponential function. Now, we have to reconstruct it from these plots. What is the key idea is that previously we had a mathematical representation, Matthew. We were assigning 3 key points. Now it's vice versa. We have to get 3 points from this plot in order to find a mathematical representation. That's why it's the reverse. Now, in order to do that, I'm just gonna go, for example, from these two. I'm gonna, in the graphic paper, I'm gonna localize the points of interest. Always the first key point, the easiest point to find is the intercepts, the y-intercepts. Imagine the y-intercepts that we have. It has an x of 0 and the point 2. Imagine I have a graphic paper, it's easy to find them. I look at the paper, I say, okay, it's 2 along the y. Now, as always that we have, for example, imagine if the x is 1, we measure the y of this point. On the graphic paper, for example, it represents the point 1 and 6. Now, I again use the graphic paper. I say that if the point is 2, I measure on the graphic paper, for example, it represents by what? By 18, which represents the point 2 and 18. The choice is yours. You can just choose any numbers you want on the graphic paper, but there is a huge however here, that the points that you pick from your plot, they have to be successive numbers. Don't get one x0, one x5, the other x9. Take 3 points which they are coming successively as an integer. For example, 3 points that are standing close together. For example, the points 0, 1, and 2. I didn't take the point 0, then choose a point 4, then another point 18. No, 3 points standing close to each other, 0, 1, 2. If that's the case, let's show them on a chart. Guys, how much time do we have?
7 minutes.
X and Y. We have X as 0, it is pointed as 2. We have X as 1, it is pointed as 6. And we have X as 2, which is pointed as 18. Now, from here, listen very carefully. It was step number 1. In the graphical paper, pick up 3 successive points. Step number 2, see how the value of the y is formed. What do I mean? Oh, fantastic answer. Thanks, Elisa. Look at this. As Elisa said, from 2, in order to go to 3, you have to multiply it by 3. From 6, in order to go to 18, you have to again multiply that by 3. This is always the case with exponential functions. The base is always constant and it is always multiplied. Then as a result, we go back to this skeleton. This skeleton says that, okay, we do not know what is y, we do not know what is a, but from our observation, we have a equals to 3. Because every y, that's the reason I said that be careful to pick up 3 points that they are successive, coming shoulder by shoulder. But also, I do not know what is the x. And that's the skeleton, which is a little bit modified. We say that, Simo, what was the problem so far? The problem was that we were looking for the mathematical representation, Ronald, which describes this plot. So far, we are okay. We were able to find the base. And this is good. The base is bigger than 1. That's a characteristic of this plot. It's increasing. Now, the other thing is that, what is the value of the a? X and y, they are part of the functions. But we need to know a, because the exponential function is, yes, please. Because the exponential function is made from the exponents a and the base. How to find the a? I say step number 2. I randomly select the point. From here, look at that, we have 3 points, point 1, point 2, point 3. all these 3 points belong to this family. Means that if I put them into the function, it satisfies the equation. Then as a result, I'm a lazy guy. I say, okay, I pick up the easiest point. What is the easiest point here? Is this point, that the x is 0. Imagine point A, which is 0 and 2. I know that it should satisfy this equation because this is part of this plot. They are part of the same family. Then as a result, I substitute it into the function. It means that this one, it's representing the x. This one represents y. Let's do the substitution and we are done for today. Then as a substitution, it becomes what? What is the value of the y in this point? 2. I do not know the value of the a. I have 3 as a base is always there. What is the value of the x? 0. Thank you. And now, let's simplify that. I have 2 equals to a. What is the value of 3 raised to the power 3? 0. Now, any number to the power 0 becomes 1. Thank you. And thanks, Daphne. I noticed that you were giving the answer also. Then as a result, it becomes a times 1. A times 1 becomes how much? A. Then as a result, we notice that we got a equals to 2. Wonderful. Because we were asking what is the value of the a as a coefficient, Sabrina. And we got it there. Then as a result, we notice that the mathematical representation of this plot, it has to be 2 times 3 as a base raised to the power of the x. And that's what we wanted to find. Choosing 3 successive points, we are done. Any questions? If no, thank you very much, guys. Then I should see you. No problem, Elisa. Let me stop.